In mechanical optimization and design optimization, when we're looking at this, we really don't have a sense of what it's going to do, what its function is, other than it rotates. At this point, there is no drive mechanism, there's no motor, hydraulic, linear actuator, water power, take your pick. Just that this is capable of rotating, and if I go over here and I suppress out the parallel, that this is able to rotate, and depending on what orientation it gets into, it can pretty much just be a back and forth motion or have that rotation. If we were to assemble this upside down, then it'd be going the other way. So a couple considerations in our design is, do we need these 8 holes, 7 holes, 2, 3, 4, 8 holes, seven instances? Could we eliminate this L shape altogether, because this is a lot of material to remove if we are traditionally machining this, and we're probably not going to find a piece of material that in an L shape that is this thick. We're going to start off with a 1 1/4 by 1 1/4 piece and remove that material. So that being the case, if we can take this off, then we could put some quarter 20s M6 by 1.0s across the bottom and probably end up with the same effect and have a little more clearance. Now if it's a side loading issue, then that also comes into the bearings. So we have to decide how we're going to drive this. If I'm going to put a motor, chances are, because of this complete rotation and the arm moving back and forth, there really won't be much out here. So rather than build a complete another assembly to mount the motor to and have it drive from this side, I would probably look at either extending something out, or whatever plate this is mounting to, having the motor kind of over in this direction and a shaft coupler coming over to the face. So let's see if we can. We'll go over to a McMaster. And so there's quite a few in the Phoenix area, with most of the components coming out of LA, or I believe Reno, sometimes Chicago. It is a pretty quick turnaround to get a lot of pieces. There is, if I'm pronouncing it right, I'm not going to be able to pronounce it right, Missimi, and Granger, and a variety of component clearinghouses. So if I could just go into bearings, you're going to see that we have the roller bearings. These are a little bit too big, and we probably don't have the RPM necessary to really justify. So these are going to be taking the rotation. Thrust bearing is going to be an end or an axial loading. And then when we have the sleeve bearings, those are going to be kind of low to medium RPM, not a lot of heat, oil embedded. Sleeves already have been soaked. The bronze has been soaked. And so if it's just carrying the load, we'll do a straight sleeve. Otherwise, we'll do the flange, because it will also have that ability to take that axial direction as well. And so we go look for our components. And so extending this piece out, we'd have to make this a little bit bigger to accept the sleeve so that this can rotate. Once we've done that, and if I decide to do both, all right, if we do both of the pins, it doesn't really need it on the other end just yet, but we're going to have to come up with some mechanism to contain it. So on this side, we would need a drive mechanism. So let's just do a couple quick modifications, and this can be where we start to use configurations. So I can do what if scenarios. And if I add a configuration, then maybe this is the drive pin. And we come up with a little bit better names as long as when we get to that kind of final stage, we've resolved all those issues and are good with our naming and our numbers. So depending on how we set up our dimensions, if I have the overall of 17, alright, that one's going to be a little problematic with changing the 10. I want to make that a little bit longer. I have an overall that's driving, so I'm really just going to need to get into that sketch. And this would be one of those instances, well, I'm happy with the 5. I could go, I'm not sure I want to get rid of the 17, so if I come over to other and let it be driven, that will cause part of the sketch to go under defined. And then we can add a dimension of 2 millimeters. And then when I change this dimension, we have this little box that says, are we changing it for all configurations or just this configuration, or specifying certain configurations if we have more than one. So maybe this goes up to 50 millimeters. I don't know, just throwing out a number. Alright, makes it pretty big. Also going to make it interesting to manufacture, having that much shape. When I save this, I go back in and let it rebuild. Nothing really happened because we haven't told it anything. So this box on the top, once we have a configuration, now I can switch it to the drive pin, hit OK, and I have something that I could mount the motor to. Alright, so these outside holes probably aren't as useful, maybe even in collision. We open that up for a sleeve bearing or flange bearing. How are we going to retain this? Are we going to rely on the motor? That's putting stress on the motor. Maybe I want to put a clip. So we do have some clip geometry. Let's see if our add-ins are active, and we'll turn on the SOLIDWORKS toolbox and let that load. And somewhere we have cams, grooves, and structural steel. So if we go into the grooves, we're going to be looking for an O-ring or retaining ring. So our retaining ring, it's a heavy-duty external, light-duty spring ring, light-duty internal. Let's go with the light-duty. One of the issues is, since this is turning, if we have that flange bearing, if that clip catches, it could potentially saw through our material. So we have to be aware of RPM, lubrication. There are a lot of little things going on here that we have to account for. Alright, so ½ inch, that'll probably get us pretty close. Groove of 472. I'm going to switch back over here real quick. And this was 10 millimeters on the, well, groove of 472 is not going to do a whole lot then. Let's see, since we're in metric, let's switch it over. Groove diameter 9.4. Alright, so it recognizes it. Width is 0.7 and radius is 0.1, so about 4 thousandths in the corners. So let's go ahead and create it. It's going to create a sketch in our geometry. And then when we hit done, now we have to place it. So I need that thickness. Oop, got a little carried away there. Ah, there it is. So we're 10 millimeters on the thickness, so I need a little bit of clearance. We're going to keep it from moving too much. Alright, so we can come back in, set our distance, and maybe I'll make that 10.1 millimeters just to have that little bit of clearance. Alright, so not seeing, usually makes this as a revolve. Alright, so let's go ahead and, since it's not defined, we're okay with that. I don't have a center line, so I'm going to go ahead and put one in. And get that out of the way. Now we can put in our diameter, 9.4. Alright, so just some really quick modifications. I would expect, well, since we don't have a relation, we're going to go vertical. And then same thing here, horizontal. And the outside really isn't that critical, so I could pick something that just ensures that it's going to make the cut. And we go ahead and accept. Alright, so that gives me a retaining ring. While we're here, I'm going to need to be able to drive that crank arm, because now this is rotating inside of the flange, and whatever adjustment we make for the flange diameters. And then the face, let's go with a plane. So I'm going to, the easiest way to make a plane, let's look at the front showing up, and that bisects the part. So I'm going to drag this out, and that goes to start a new plane, and then we can go parallel, and the next reference will make it tangent to the cylinder. Alright, so on that plane then I can open up a sketch, and let's say we're going to use a 3mm 1/8" square stock. So I'm going to select the midpoint, hold down the control button, put midpoint to midpoint, and I think we're probably going to end up with 1/8". So, and it's in metric, so 0.125 inches. So that'll take me over to the 3.18. So I need to type in IN. There we go. And one of my preferred favorite is to make that construction geometry. Come over and pick up a tangent arc. Connect the endpoints. And then, because when we manufacture this, we're just going to have this segment for the pin to sit in, then that will create our depth, and pretty much an 1/8" end mill or a smaller end mill would be able to go in there and open up that geometry. Alright, so when I make this cut, this is going to go about 1.5 mm. So if I just do the 0.62 an inch, so basically half of it goes into the shaft, half of it goes into the bore, and we can hide the plane, and that gives us enough to drive our geometry off. So some quick modifications to start looking at the power transfer and being able to manipulate these geometries. Right, so, and if I decide, hey, that's really not the way I want to drive this, I'm going to do something over on the other side, I can always go in, put this back to the default configuration, and my what if scenario takes a different turn. Alright, so looking at the crank, manufacturing the dog bone shape has a couple of extra steps in it. We're either, being that it's 5mm thick, that's a little heavy on the stamp. We could stamp these if we were making a lot of them. If we're going to machine them, when we look at the manufacturing process, we would have to hold on one side while it goes around, and then flip the clamp over until we got the holes in it, or we'd have to drill the holes first and then clamp through the holes, and then we could go all the way around. There's probably some better, different ways to look at that geometry. So from a loading standpoint, the advantage of the dog bone is it removes weight, but it gives us a linear beam right through the center of the part. Depending on the loading, I don't know that that's 100% necessary. So let's look at a design revision, or again, another what if scenario. And I'm just going to stay in, well, I guess I need to, all of our numbers are in metric. Alright, so we have the radius of 9, so 8 millimeters or 18 millimeters on the outside, and let's see, so that would be 72. I'm probably going to bump that up so that we can use a piece of 3/4 material, 3/4 of an inch, so that 19 millimeters actually ends up to be about 748. All right, and then our lengths and sizes. So we're going to start with the same basic process. Open up a sketch, and here I can do a center rectangle. And again, if I go to construction geometry, now when I pull my tangent arcs, we can go through the centers and missed. It has to connect with a tangent arc. Okay, so very quickly I can create some geometry. And I'm kind of cruising through these, making relations, setting them to equal. So we said this is going to be a radius of 10 to go with our diameter of 10. Alright, so I'm optimizing in this case for the material size, being able to take it off the off the rack piece of material, not have to do anything to the sides, make a radius on the end, put a couple holes in it, and then pretty much be done with the part. So our sizing, circle to circle, I believe the first one was 50. And we'll go check that real quick. So we have 50, 80, and 160. And to lighten, if we really aren't, if we are concerned with weight, where the other side, or the dog bone kind of removed to the outside, we could always put an knob round in the center. So the center point straight slot. And I could remove material that way to lighten the arm. But if we don't have that concern about weight, then we'll just go ahead and extrude 5 millimeters and OK. So going back into the configurations as another introduction is, if we call this one, well, let me just make a new configuration. So we always want to add the configuration from the top level. This is our 50 millimeter. The default can be whatever. So whichever one we built first. And then I'm going to add the configuration for the 80 millimeter. And I don't remember what the name was. We had connector and follower, coupler and follower. Alright, so the coupler was the 160, so 80 millimeter. Still trying to get those backwards, so coupler, and then one more, and 160 millimeter follower. Alright, so what we can do is, utilizing those, we're going to set for this configuration, and I was in the 160, and when I rebuild it, it'll take me out to size, and then the 80 millimeter, let's see if we can specify. We'll utilize that one real quick. So if I don't go back in and say specify configurations, this is going to be applied to, cannot deselect, oh, okay. It's gonna make me pick all of them, so that would be the default. So let's just go into the 80 millimeter, jump back in, 80, and this configuration, and OK. So to check for the configurations, we go through each of the items in the list over to the configuration tab. 50 millimeters, shrinks it. We were just at 80, so 160 lengthens it. And now we have something that's a little bit easier to manufacture, and we would have to replace. So I'm gonna just do I'm just going to call this the arm. So, all right. So coming back to our drive mechanism, on one side this is probably going to be the rotating, or I can't really drive on this side. The other item's going to have to. So on the 50 and the 80, we're going to potentially have this this notch for the square key. Alright, so if I put those in, I put in a square key. I didn't quite get to the quadrant, so we're going to make that horizontal. I'm going to set these to equal. And 0.125 inches. And then when we cut through, now half of the geometry is into the shaft, half of the geometry is into the base. When we cut this, it will go through. Now I'll just do up to next. And now I have something that's capable of driving. So that's going to be a broach operation or some type of operation to relieve that notch. All right, so that's going to match up with the arm and the key weight to provide a drive mechanism. All right, so some different mechanics to start to look at how this thing is actually going to operate.